All right, y'all. Good evening. Welcome, welcome. So, fourth week, y'all. 3 weeks down, and in my opinion, we're past some of the worst weeks in this class. Yeah, vector stuff. We've gotten through kind of the vectors. And if you've started the problem sets for voltage and potential, you'll see that mathematically, in my opinion, it's much easier to solve than the vector stuff. So hopefully it'll be a nice breather. Honestly, the stuff we're kind of covering for the next little bit in general is not going to be too mathematically bad. Next week in particular, we're actually be pretty light, and this week is not too bad. So, forces, electric fields, in my opinion, that's some of the trickiest stuff to begin with. Hitting you all with a bunch of concepts, we'll also have to do stuff with vectors. So again, we're past that. Now, I say past that. We're past kind of covering it. You've hopefully kind of done most of the work for it. So at this point, hopefully just kind of polishing up your skills in those areas as we get closer to the test. So the test, we got this week and next week as far as content is concerned. But reminder to you all that our test will be this Thursday. Not this week. February the 15th, this Thursday, meaning the one I'm pointed at on the screen, February 15th. Really make certain I don't get a bunch of emails from people freaking out. February 15th is our exam, so we have 2 weeks. So we'll get through what we can get through. We're going to get through everything. That's going to happen. But if we have any extra time on this Thursday, we'll start reviewing stuff. But definitely on the 13th, so we're on the 8th, if we get through stuff, we'll start reviewing. The 13th is just going to be review. One of the things I mentioned to you all a while back when I was talking about the course is that for the test, you are allowed to bring a 5x8 note card with whatever you want written on it front and back. So if you didn't know that, that's a thing. So starting next week, I will start bringing in those note cards, and you can put literally whatever you want on it. You can draw some pretty pictures. You can write positive messages to yourself. You can write physics on it. I don't care what you put on it. The only thing you're not allowed to do is staple a bunch of flip book papers to it. So you can print stuff and glue it flat to it. I'm cool with that. If you prefer to type up your stuff or do it digitally and then print that and then glue it flat, that's fine. I just want to give everyone the equal opportunities to know flipbooks. Front and back is cool. Now, I will also give you a formula sheet on this test, and I've uploaded what that formula sheet is. So that is available if you go to the Files tab. Here's the formula sheet. Now, when you open this up, you're going to see a lot of equations we have not learned yet. That means you don't need them. But they're going to be on here because this is the same formula sheet you're going to use for every single quiz. Is going to use the same every single test. It's going to use the same formula sheet. This is every single equation you are going to need in this class in one go. Now, it's an order of what we've learned. If you look here at the top, there's constants, sure. There's mu naught, 4 pi times 10 to the minus 7. There's, did I not put k? Okay, I'll add k on here. 9 times 10 to the 9. I'll add that. I'm not sure what happened here with H. That's kind of funky. But everything, mass of electron, mass of proton, charge of electron, charge of proton, all of that is here. There's Planck's constant. I don't know why that's in there. You don't actually end up using Planck's constant. Epsilon naught, the speed of light, that's going to come into play way later. I'll add k, 9 times 10 to the 9. You probably have it memorized by now, but I'll put it there just in case. And again, you can see here's the charge, the net charge equation, force, electric field, there's flux. Again, you can kind of see the things we've learned by looking over this. Potential energy, which we learned last week, conservation of energy, potential energy in terms of voltage, kinetic energy, just the general equation for it, voltage, aka potential, not potential energy, potential. For a point charge, the relationship between voltage and electric field, and hey, look, there's the stuff we're covering today, capacitance and things of that nature. So, this is available. Feel free to kind of have this whenever you're solving any problem, or you use your notes, whatever you want to use. But this exists now, so you do not need to put any of this on your note card unless you really want to. You will get this during the test. So meaning if you don't bring a note card, you still will have the equations. So whatever you put in your note card, if you want to put these again, go for it. If you want to clarify any of these, go for it. You want to draw pictures of what these look like, go for it. Do it. That's up to you. But just know that I will provide all of this to you on the test. Okay? So it gives you a sense of what you will have at your disposal. I'm going to send out an announcement about the test sometime tomorrow. So the details, just so you all can prepare for it mentally. It's going to all be done during that class period. It will be 20 questions, multiple choice. That will make up 80% of the grade. And then the other 20% is there will be 2 free response. You will choose one of those to solve. You get to pick which one. Okay? Those free responses will be a more involved problem. The free responses will have a partial credit associated with them. Again, I'm currently planning on making that 20%. I'm going to think a little bit longer. At most, it would be 30%. But I'm thinking 20% for that problem, whatever one you choose. That's what I did last time, and it worked out pretty well. So that one, partial credit. I will post the rubric for that as well, as far as how partial credit's determined. But it's just the 4-step problem-solving process. How was your picture? Did you write down your givens? If you did that, great. There's some points. Did you identify the missing? There's some points. Did you write the relevant equations? There's some points. Did you plug the right numbers in the right spot? There's some, again, every step in the process, you earned some points if you did it correctly. If at the very end of the problem on that free response, you did everything right, but you just flubbed the math in your calculator, like you wrote it perfectly, the equation for it, and you just maybe hit the wrong button in your calculator or something silly like that, you only lose a couple points out of the 20. Literally 2 points out of the 20. So, remember, the math is not what I'm testing you on. I'm testing you on the process, and the rubric will reflect that. Now, the multiple choice, it's all or nothing. Like, you either get it or you don't. Because it's multiple choice, there's some test skills that you can kind of use. So, a reminder to you all, one of the answers will be correct. Meaning, if there's algebra involved, you can literally take the answers and plug them in and see which one works out algebraically. That's a thing you can do. You will know if your answer is wrong if it's not one of the ones listed. So it kind of reveals that. And then, that's kind of the major test skills. You can see if the questions, go back to them, all that kind of jazz. A, B, C, D, I don't think any of them have an E option. So you got a 1 in 4 shot of getting it right, even by guessing. But yeah, that worked out pretty well when I taught this class last spring. That's the plan. Time-wise, 20 questions with the free response seemed to work pretty well. Now, unfortunately, I did tell you all a while back I was going to post the old test. It doesn't seem like I'm going to be able to do that because I've kind of leaned into the camp of I want to look at my old test and I want to see which questions were really bad and not ask those, and then basically take the ones that were pretty solid. Now, which questions are the ones that are really bad? The ones that everyone missed. Like, that's an indication that either I didn't teach it well, that's on me. That's a pro tip. That is my perspective on teaching. If everyone in a class fails at something, there's only one common denominator there. It's me. So that means that something went wrong on my end. So, again, I apologize. I said I was going to post a test. I'm not going to end up doing that because I'm going to actually use that to kind of pick the best questions possible based on what seems to have a good distribution of difficulty, and also to make certain that the timing works out well. It seems like a small thing, but making good questions is a skill in and of itself, and takes time to refine those questions. So, anywho, there's that. If you have any questions, so again, I'll make the announcement. We'll post it. So you have all the details for that test, and yeah, it'll be great. So, any questions about anything I just said? Cool. All right. As usual, if you have questions at any point, email me. But yeah, make certain you are staying on top of the older stuff. If you are having challenges, and this week 1, week 2, come visit me in office hours. Come, polish those up. Don't just forget about those things. They are important. So keep those in mind. So last class, to give you all a recap. Here's what we learned last week. Here's a nice little written recap. We talked about voltage. Potential. So we first started with electric potential energy. Electric potential energy. And that was U. U subscript E because it was due to the electric field. The E doesn't stand for energy. The E stands for electric field. U stands for potential. Electric potential energy. And then we introduced something called potential. Electric potential. And I really, really tried to hammer into your all's heads that these are not the same thing. these are not the same thing. They are two separate things. Electric potential energy is U. Electric potential is V. They have a very nice relationship between them. UE equals QV. So clearly they're not the same thing, because if you multiply that V times Q, you get U. So anyway, but very, very important. This is one of the most common mistakes that may happen on the test, is I say find the potential at some point. And then people ask, doesn't there need to be a charge there to find the potential? That's because they're thinking of potential energy. And then I'll come around and say, nope, you have everything you need to solve the problem, blah, blah, blah. Another name for electric potential is voltage. They mean the exact same thing. Voltage, electric potential, same thing. Voltage, electric potential energy, not the same thing. Again, really just, as you solve these problems, you'll discover which one you'll realize it. As you're solving them, if it says find the voltage, you cannot use an equation. Don't solve for you. Anyway. And then we define this electric potential difference as delta V. And really, anytime we talk about voltage, it's always a delta V. It's always a final minus initial. So for example, when you talk about your battery, you have, AA batteries traditionally, I think 1.5 volts. So here's my battery, it says 1.5 volts. When it says 1.5 volts, what it is actually saying is the difference between those two sides is 1.5 volts. So let's just make up some numbers. The easy numbers to make up is that this side is 0 volts. And by extension, if it's a change, then this side's 1.5 volts. That's one example. Or I could have 101.5 volts here, which would make this side 100 volts. The numbers here by themselves don't mean much. It's the difference that matters. It's the difference in voltage that makes all the difference. The difference between the two sides makes all the difference. So we're going to see that as we solve problems. Just having a voltage does nothing. You need a difference in voltage for anything to happen. Literally the first problem I'm going to do for y'all today is kind of a recap of this. And it's going to kind of talk about this. You need a difference in voltage for anything to happen. Easy example of this, easy analogy. You all need a difference in height for anything to fall. Who cares how high up you are? You're not going to fall if there's not a lower height for you to fall to. You could be 1,000,000 miles up. If you're on a flat floor and there's nothing lower than that, you're never going to fall. So, height is kind of like this voltage in the sense of height is relative. Anytime you talk about height, even when you say how tall you are referencing the top of your head to the bottom of your feet. There is an implicit between 2 points. When you say how tall anything is, you're referencing from some spot to some spot. And that's kind of implied, and everyone kind of has that understanding, but that's just something to remind you all of. Even height, just like voltage, it's always a difference that actually matters. Anyway. So, last thing as well, this is just one of the rules of the universe. Everything wants to go lower potential energy. This is the reason things fall. This is also the reason, another explanation for why charges move. Another explanation. We have electric fields as one explanation. Things going to lower energy is another explanation. And we talked about positive charges go from high potential to low potential. And negative charges go from low potential to high potential. And you may look at that and say, but wait, you just said they always go to lower potential energy. Lower potential energy. There is no energy word here, just potential. So again, that distinguishing between potential. If it seems like I'm spending a lot of time on this, that's because this is one of the most common mistakes people make in this area. The math is not hard, but if you mix up the words potential energy and potential, it doesn't matter how good your math skills are, you're going to use the wrong equation and it's all going to go to crap. So, that's why I'm spending so much time on this, because the math here is not bad, but just this one little word difference throws off so many people. Anyway, so let's go and do it. Yeah, and the last kind of tip I told you all, if you see speed or velocity in a problem, you're going to use conservation of energy. That's going to happen. That is, your mind should immediately go to, bam, that's a strategy I'm going to use for test one. When we get to test two, we're going to talk about other kinds of velocities. But the problems will be so different, they won't be talking about voltage at all. They'll be talking about magnetic fields. That's in the future. That's a future problem. For test one, if I see velocity or speed or meters per second, which is the units for those, immediately you should say, I'm going to do this. My energy, my potential energy initial plus my kinetic energy initial equals my potential energy final plus kinetic energy final. And what this also kind of boils down to is that my change in potential energy equals my negative change in kinetic energy. Literally all I did was just shifted things around. Final minus this, so I moved that one here, and I moved that one here. All I did was shift these things around. Final minus initial, and then if I move that around, final minus initial equals change in kinetic energy. So we're going to see that an application in the next problem. But again, I'm spending the time on this because we actually have a good amount. We're actually pretty flexible right now in terms of time. The next I'm going to cover is not going to be too bad. So let's go ahead and apply this. So evacuated tube, that just means there's no air in it. Uses an accelerating voltage of 44 kilovolts to accelerate electrons to hit a copper plate and produce X-rays. Ignoring relativistic effects, what would be the maximum speed of these electrons? Speed. Conservation of energy is going to come into play. Immediately, just like we know it's going to happen. All right, so we don't have voltage per se. We have the change in voltage. Remember, voltage is all relative. Who cares if I have 44,000 if there's not a spot that's zero? If I don't have it. So whenever you hear the word voltage, it's always a change in voltage, really. So if I have an accelerating voltage, that means at some spot, it's 44,000 volts. At some spot, it's 0 volts. That's the key here. Otherwise, if I just had the 44,000 volts, nothing's going to move. Again, if there's no place that's lower, if there's no place with lower energy, nothing's going to move. Again, this is potential, not energy, but they all connect. Anyway, so it's going to be the change. We kind of got to get used to seeing that voltage, that it's going to be a change. Volts, I already converted it from kilovolts to volts. Anytime you see a prefix, you got to convert it. All right, we got electrons. We know the charge of an electron is negative 1.6 e to the minus 19 coulombs. We know that the mass of an electron, we're going to see where we need that in a second. You know what? Let's just pretend like I don't even know that I need mass of electron. I say, I see electron, I think charge. Let's just see what happens. All right, we're solving for the maximum speed. So we'll call that V final. It's getting faster, so we're solving for the final speed. And again, because we saw the word speed, because we saw that, we immediately know, all right, conservation of energy. Potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. I am not going to give you any problems where there is both electric potential energy and gravitational potential energy. So that makes your life a little easier. And again, I'm actually going to write this the way I wrote it last time. The change of potential energy equals the change in kinetic. Because the reality is almost every problem is going to boil down to this. You'll see what I mean when I set it up. We remember that the change in potential equals Q times the change in voltage. U equals Q times V. But again, we're putting those changes there because that change is a more appropriate way to kind of look at this. And good old kinetic energy is 1/2 mv squared. Okay. So we're going to make a substitute. We're going to go ahead and plug those into the equation. Now, one of the things you can assume is that these electrons are, it doesn't explicitly say it here, but it basically, if it doesn't say it, you can generally assume it. These electrons start at rest. They initially are not moving. If they are moving due to something else, then that's, I don't even know what that other thing would be. We're going to assume these things are at rest. They start at rest, and then they get accelerated. That they're not originally moving to begin with, because otherwise this would be impossible to solve. So if they are at rest, then my change in kinetic energy just is 1/2 mv squared. You know, I'll go ahead and write this out just to make this clear. So great, we got Q delta V equals 1/2 mv final squared minus 1/2 mv initial squared. If it's at rest, Boom. If it starts at rest, then my initial velocity is 0, so that term goes to 0. Because velocity initial is 0. Again, I'll put that. And this is really what every single one of these problems boils down to. Almost every one of these every single one of these conservation of energy, Q of E equals 1/2 mv squared. They basically all boil down to end up being that way. I will not be giving you a problem where it starts at 3 meters per second and then ends at a later velocity. I'm just going to have them start at 0. At the end of the day, really what I'm testing is, do you understand? Because you all did plenty of conservation of energy problems in Physics 1. They had all the starting velocity, final velocity, heights, and all that jazz. I am wanting to see if you all understand that potential energy is Q times V. That's the new thing for you all. That's the new thing. And Jim just connecting to something you know. So at this point, we look at our equation. We said we're solving for final velocity. Fantastic. There it is in all its glory. We say, yep, we got Q. Yep, we got delta V. Do we have the mass? And this is where I said at the beginning, I started to put it and I was like, maybe you wouldn't, how would you know that you even needed the mass of an electron? Sometimes when working through the problem, you realize, I need this. We say, mass. What's actually moving in this? What's actually gaining this energy? An electron. Maybe I should add the mass of an electron as one of my givens. And we can go back and do so. And if you're like, man, I don't have that memorized. Good news. No, this is the wrong formula sheet for y'all. Boom! That's the one for Physics 1. There it is. It's in the formula sheet. 9.11 times 10 to the minus 31. So in a problem on the test, it may say, you may need the mass of an electron. You may have to look at the formula sheet. It may not say that in the problem. Mass of an electron is 9. But it's given in the formula sheet. So it is there somewhere. It is on your test somewhere. All right, so great. 9.11 times 10 to the minus 31 kilograms. And at this point, y'all, it's just plug and chug. So negative 1.6 e to the minus 19 times this 44. And I forgot something here. This negative here was a little important. This negative here is important for us because it's going to cancel out that negative and make us happy. I'll go ahead and tell you all, if your negatives don't end up canceling out, just pretend like they do for these problems. When you're solving, because we kind of talked about this a little bit. We have kind of talked about this, that electrons will go from low voltage to high voltage. Protons go from high voltage to low voltage. And great, that is useful to know, and there will be conceptual questions on that. But don't let that get you hung up on this. If you're trying to solve this problem and you have a negative on this side, when we inevitably do a square root, you're doing the square root of a negative. Pro tip, if you're ever doing the square root of a negative, you probably just accidentally put a negative where you shouldn't have, or something should have worked out. That's just a physics thing. Obviously, I'm never going to have you do the square root of a negative number, so you can almost just pretend that the negative somehow should have canceled out and pretend like it's not there. It sounds silly, but trust me, at some point, you're going to end up with a negative that you shouldn't have. And sure, you can look back, see why that happened, all that jazz. But the end result will just end up being, I forgot to put a negative here, or something silly like that. Move on with your life, especially on the test. Don't get too hung up on that. It's not worth the time and energy. All right. 9.11 e to the minus 31 times velocity final squared. Now, I'm at this point kind of just thinking, man, is it really worth me plugging this in the calculator and spending the time? And the answer is yes, because there is always one final step we need to do, and we can't do that final step until I get a number. And that final step is, does my answer make sense? You should always check if your answer makes sense. So I'll get the answer and we'll practice that skill together. Let me shrink all this. So we call it the 4-step problem solving. I call it the 4-step problem solving process. You call it whatever you want. Write down your givens, write down your missing, find the equations that relate them, plug and chug. But really it's kind of a 6-step problem solving process, which you're like, what? Draw a picture if possible. If possible. It's not always relevant, but when it comes to vectors, you should draw pictures. Any problem involving vectors should have a picture. So draw a picture, then go through the 4 steps, and then the last step is not just writing the answer. The last step is always, does it make sense? The beautiful thing about physics is it's not just a math. I mean, we do a lot of math, but it's math that means something. And so your answer should make sense. That's a way to check your work. So we get 7.04 times 10 to the minus 15 equals half of the other side. I'm doing the simplification before I do the algebra. Next, I'm going to divide this over. So divide 4.56, e to the minus 31. Divide 4.56, e to the minus 31. And then we're going to square root that to get rid of the squared. So I will do 2 steps in one. We got to get rid of that squared because it's not VF squared I'm solving for, it's VF. And we should get a velocity. And this is a wild number, y'all. Absolutely wild number. You may not realize. One, it's huge. Like, that should be obvious. That's a big number. 1.24 times 10 to the 8. Huge number. I mean, that is, move that decimal 8 places. That is 124 million meters per second. It's very fast. Okay. May not know this, but we'll learn this at some point. There's a speed limit to the universe. Thankfully, we have not exceeded that speed limit, so that's how you check if this makes sense. 3 times 10 to the 8 is the speed of light. This is below that, so we're okay there. And then you may ask yourself, is this reasonable? This requires a little bit of background knowledge for this problem. One, that's a huge voltage, 44,000 volts. That's obviously a lot of voltage. You touch that, you die. We're producing X-rays, and this is actually, it's a nice medical kind of connection. X-rays are dangerous. Now that may seem counterintuitive. I don't know how much y'all learned about X-rays. You get them low to your bones. They're high energy. They will cause cancer if you get exposed to lots of them. But to make these X-rays is not a simple task. You need a lot of energy. These X-rays have a lot of energy, so we got to put in a lot of energy. This electron has a lot of energy. It's moving real fast. So that's kind of the connection here, which is kind of interesting. So, yeah, I'll try to give you all more problems that are a bit more reasonable. In general, high voltage, 44. When you get to the kilovolts, that's a lot going on there. It makes sense we're going to get big numbers in the kilovolts. When we talk about coulombs, 1 coulomb is a lot of charge. That's another reference for you all. 1 coulomb is a lot of charge. You know how big a meter is. Forces. Well, when I review for the test, that is honestly something I'll spend the time on. What is a reasonable answer? It's worthwhile. All right, so there you go. It's fast, but we're not breaking the speed of light, so that's kind of the big takeaway. If our answer was 4 times 10 to the 8, nope, impossible. And the reality is the answer would technically be lower than this. When we get close to the speed of light, things get wonky, but for us, it's fine. All right, great, fantastic. Review, voltage, electric potential energy, all that jazz. Good things. So today and tomorrow, we're going to actually start getting into practical uses for these things. Specifically, the components that make up circuits. So today, we're going to do capacitors and resistors. And then kind of next week, I believe we're going to start talking about resistivity and start to get into circuits a little bit. And when we get back after test 1, we'll start to talk about circuits, which are wires and electricity and all that kind of stuff. So starting to take these ideas and actually build useful things with them, our society requires electricity. If the lights went out, a lot of people are going to die. It is critical to sustaining our current world. So anyway, capacitors and resistors are key components of this. We'll talk about what they are today. We'll talk about how to calculate the math for them. And they're really simple. Again, physics is all about building from the ground level up. So you're going to see today that these are very simple based on base principles, nothing too fancy. So yeah, what is a capacitor? What is capacitance and how does it relate to voltage, charge, and energy? Again, the last 3 words are words we've seen before. Where the resistor is, resistivity, and we'll calculate the resistance of resistor. That'll be great. Super simple. Won't be bad at all. All right, so what is a capacitor? It is something you've seen before, and you may not have even realized it. 1, you've probably seen it in circuit diagrams, but 2, It's using something we learned in class. It's 2 plates. So if you all remember from electric fields, we had a plane of charge, and we found the electric field due to a plane of charge. Take 2 of them, and you got a capacitor. That's all a capacitor is. 2 planes of charge. So that's why I mentioned way back when I said you got a line of charge, a plane of charge, and a sphere of charge. And I made a little bit of hullabaloo about the plane of charge. This is why. It actually comes up later. We will not use a line of charge or a sphere of charge for anything, but it was worth mentioning them. All right. All sorts of applications. So these are everywhere. I mean, obviously they're in like circuits. They're the, if you ever look at this, do I have a picture of what they look like? Yeah, there they are. If you've ever seen like a circuit, and you've seen these little like cylinders in it, those are capacitors. Now you may be like, those don't look like 2 planes. So going back to my previous picture, if you take 2 planes and you put something between them and you roll it up, you've made a cylinder, and that's just more efficient space-wise. That's literally just take this and roll it up. And ta-da, but it works the same way mathematically. But more efficient. More efficient. Anyway, so yeah, stud finder. Car amplifier, lightning, defibrillators, your phone touchscreen. It's how it figures out where your phone is. Your finger acts like a plane, and then the other plane's inside your phone, and it does the math. Old-fashioned camera flashes, big circuitry. Basically, here's what they're used for. Anytime you need a lot of charge really quickly. Anytime you need a lot of charge really quickly, that's what a capacitor is. You can almost think of these things like a bucket filled with water, but instead of water, it's charge. And you can imagine taking that bucket and dumping it, and you get a lot of water real quick. That's what these things do. You fill them up real quick, and they can discharge really quick. The capacitors, or the defibrillators, you'll see them kind of rubbing together, and it takes a little bit for them to kind of do their thing, and then they say clear, and then they bop. When they bop someone with it, it just releases all that charge really quick. So these things are just a way to hold a bunch of charge real quick, and that's useful for all sorts of things. So we've learned about charge. If we build up a bunch of it, we can do all sorts of cool things, like starting/stopping someone's heart and all that jazz. So yeah, there they are again. It's just some pictures of them. We'll get to this in a second, so don't worry about that picture. But just, yeah, here's what they look like. Anytime you see a circuit from the future, that's what they look like. All right. We're making some assumptions here. The real world's more complicated. We're assuming these planes are infinitely large. Technically, there's these effects at the edges, but they're so small, who cares? They really don't matter much. So we're making these. Again, you don't need to know this, but I'm just letting you know the real world's more complicated than I teach you all. Surprise, surprise. But it's good enough. We're getting like 99% of the way there. That extra 1%, that's for electrical engineers to worry about. All right. So let's see if y'all remember this. What is the equation for the electric field due to an infinite plane? You know what? Let's see if this is actually written on the formula sheet. I'm not 100% sure if it is, and if it's not, I may actually add it. Yeah, and I'm looking back at this thing, and I thought I had everything you needed on here. Yeah, it is. It's on here. All right. So what's the equation? If you all pull up the it is on this formula sheet somewhere. Is it sigma over 4 pi epsilon naught r squared? All of that in the bottom is parentheses. I'll go ahead and parentheses it so you know that when I'm doing that division there, it's everything. All right. Is it sigma over 4 pi epsilon naught r squared? Is it q over 4 pi epsilon naught r squared? Is it sigma over 2 epsilon naught? Or is it sigma over epsilon naught? A lot of Greek letters up there. But at the end of the day, what is the equation for the electric field due to an infinite plane of charge? This is not a line of charge. This is a plane of charge, like a piece of paper, at some distance r away. Oh yeah, and fingers crossed. I've been real annoyed with the technical difficulties I've run into each class. I have. So it's basically all due to the streaming. Streaming's a CPU hog. So I've made the stream worse. And hopefully that'll improve it. No more 60 frames per second, which I don't think matters for still images. And also the resolution is a tiny bit worse. But hopefully that will make my computer a little bit happier and not have those problems I've kept running into. So far it's worked out well. I've taught 2 classes before you since Thursday and they've gone smoothly. So fingers crossed. All right, we'll go to 205. At this point, kind of either you found it or you haven't. 5, 4, 3, 2, 1. Let's go ahead and look at that formula sheet I've just given you all and see if we can find it. So, electric field. You only got so many options. There's 1, 2, 3, 4, 5 equations. It's going to be one of those. We go through our options. This one here, that's a point charge. A single charge. If you want to find the electric field away from a single charge, there it is. If you want to find the electric field and you have the force on something and you have the charge, there it is. If you want to find the electric field for a sphere, here it is. Line of charge, there it is, and process of elimination. The last one here is a plane of charge. And this is the one that is very interesting because it has no R in it anywhere. To remind you all what this sigma is, this sigma is just how much charge do I have divided by the area of my plane. It's how my charge is distributed. Is it really dense or is it really spread out? Do I have a lot of it in a tight area or not much of it in a tight area? Again, it's kind of like mass density, but it's for a two-dimensional surface. How much charge per area? All right. Now let's get wild, y'all. What if I have 2 of them? Oh, man. What if I have the same one I had before? So I got an infinite plane here with positive charge. And to the right of it, I have an infinite plane with a negative charge. What is the electric field some distance away, R? And you know what? Just because to make it easier, we'll say it's equal distance from both of them. Doesn't matter. If it mattered, I would have given it to you. What is the electric field at that dot due to both of these? We'll go to 215. 210. All right, so 5, 4, 3, 2, 1. All right. So here's the key to this one, y'all. We already found, remember, if you have 2 things going on and you want to find the total field, find the field due to one of those things, find the field due to the other thing, add them together. So if you had 2 point charges and you want the electric field, find the electric field due to one, find the electric field due to the other, add them up. So the electric field due to this positive one is to the right. Let's call this E1. So this object 1, this one here over object 2. What's the electric field due to, so we're going to find the electric field of this one. Now, this is where there's a few things we need to remember here. We need to remember we could add up fields due to multiple things. We also need to remember that electric fields point away from positives and they point towards negatives. Away from positive charges and towards negative charges. Very, very important. We remember the direction electric fields point. So, if we want the net field, we're going to add E1 plus E2. Both of these point in the same direction, so they do add. If one was pointed to the left, it would be negative, but they're both pointed to the right, so they're both positive. What is the electric field due to a single plane of charge? Sigma over 2 epsilon naught. So, all right, for that one, for electric field 1, there it is. For electric field 2, same thing. These both have the same charge in the same area. You add those up, and the 2's cancel out. So that's it. It just doubled. If you have one plane of charge, it makes sigma over 2 epsilon naught. You got 2 of them, it doubles. And they add up because one's to the right, one's to the They're both to the right because they're opposite, but they're on opposite sides of that spot. So this is I like this problem a lot because it uses so many of the concepts. Oh, yeah, it's good. I love this. All we did here, and I really like this one. Check this one out because it uses so many concepts. It was just like the last one. But now we have a second one, and the reason that these both point in the same direction is because electric fields point away from positives and they point towards negatives. What's wild here is what is the electric field outside this thing? If I found the electric field anywhere else, so let's just go ahead and do that. The electric field here points away from the positive and points towards the negative. And remember, this equation has no dependence upon distance. So the electric field everywhere outside this capacitor is 0. Because there is no dependence upon distance in these equations, everywhere else the vectors point in opposite directions. If we do the same thing on this side, on the right side of this one, the electric field due to 1 still points away from 1. The electric field due to 2 still points towards 2, but again, you can see they're opposite directions. So this is a great kind of problem to understand the directions of electric fields. Yeah?
Will there be questions where they will be the same sign and then the equation will change, or it will always be
there will be, so one of my favorite questions for this concept of how electric fields point. I'm a really big fan of, and the problem set, if you kind of go way back to when we talked about electric fields, okay. So this one, it's about forces, but you could actually do this problem with electric fields and the answer would be identical. So this problem, this is number 5. Number 5, it has this picture here and it says, if I put a positive charge at each of these dots, rank them. I could have reworded this problem to find the electric field at each of these dots. You don't need to put a charge here anymore. Rank them. And this is a great problem for that. So the logic we just used there also basically applies to this one. So I don't know how much. So yeah, you may have situations where I have positives and negatives on different spots and different places and different distances. And you need to find, and we did a few clicker questions like that as well. And those are really, really good to look over. So yeah, remind yourself of direction and distance and mattering and all that kind of stuff. I don't know if that, did that answer?
Well, I mean, specifically for the plate.
Yeah, okay, so what was the plate? What was the question with the...
If they had this opposite charge,
yeah.
2 positives,
yeah,
would
so
we change our equation and solve that?
Yeah, great question. If I had 2 positive plates here, and I said find the electric field inside, the electric field inside would be 0, and everywhere outside it would be sigma over epsilon naught. So the opposite would happen. Now, I will tell you that won't end up happening because this is actually what capacitors will look like. But that is a great question. What would it look like if I had 2 positives or 2 negative planes? It would be the exact opposite of this problem. The electric field would be 0 inside and sigma over epsilon naught everywhere else. Whereas in this case, the electric field inside it is that, and everywhere outside it is 0. But yeah, we're going to just see in a second that this is a capacitor. This is the definition of a capacitor. 2 planes with opposite charge, they make an electric field between them. Another good point here, so the electric field everywhere inside this thing is the same value. Everywhere inside it is this value. At this spot, sigma over epsilon naught. At this spot, sigma over epsilon naught. Literally every single spot inside it has the same electric field. Because this is how infinite planes work. Again, we're assuming they're infinite. The reality is on the edges, yeah, sure, it's not quite that. But we're going to assume it's infinite and these things have no ends to them. So, that's what a capacitor is, and that's just what we're going to be spending the kind of time talking about. So, again, nothing really to write down here. This is just reminders that the electric field equals the change in voltage over distance. So we just need to remind ourselves of that. And then there's units and stuff like that, that 1 newtons per coulomb equals 1 volt per meter. So the unit for electric field, previously we said was newtons per coulomb. The unit for electric field is also volts per meter from this equation. Electric field is a made-up thing, and so the units come from the math. The units come from the math. So I guess voltage, you could argue, is a made-up thing. All right, why does all this matter? Why am I mentioning this? This is what matters. In a capacitor, the potential difference, in fact, let me go ahead and make this more accurate. The potential difference, oh, the joy of finding the triangle. Oh gosh, I'm just going to draw it on here and search for it later. One of my banes with PowerPoint is how challenging it is to find symbols. It's awful. It's a Greek letter. I find the Greek letters. The change in voltage equals the electric field times distance. The electric field is the same everywhere inside it. The electric field is the same everywhere inside it. So, if I know the electric field inside a capacitor, I just multiply that by the distance between the plates, and I get how much the voltage goes up. And vice versa. If I know the voltage and I know the distance between the plates, I can find the electric field. Very simple relationship, very useful relationship. We're going to see it as we kind of solve some problems with these. All right, and again here you can see this electric field. It's the same everywhere. And you can see the voltage changes. The voltage changes, but the electric field is the same everywhere. The voltage starts at 1.5 and goes down to 0, and it happens at a very uniform rate. Again, it's kind of like a hill that's got a nice, simple slope to it. The voltage changes, the electric field is constant. The voltage changes, the electric field is constant. That's at this point, we've introduced so many variables that just kind of keeping track of them. That's the challenge. So the voltage changes, but the electric field is constant. Which makes sense, because if there's no change in voltage, then it doesn't do anything. Remember, you need a change in voltage for anything to happen. And, let's kind of look at this and just see if it all makes sense. Let's see, I don't think I have a question about this. Let's make one. Let's have y'all on the fly clicker question. So, here's my plate. Here's my question to y'all. Whatever, clicker question. Alright, if I put a positive charge in between these plates, which way will it move? Will it go up, down, left, or right? And there is so many ways, there is like 3 or 4 different ways that you can answer this, like to figure out the answer. As far as why charges move, at this point, I've given you all like 3 or 4 different ways to figure it out. Go with whichever one. They should all give you the same answer. Every single option for figuring out how it works should all make sense. And so I will explain all the options when we answer this. But this is kind of a good putting a bunch of concepts together. Plot a proton, or whatever, just any positive charge. Which way will it move? And I can think of 4 different ways to explain which way it'll move. And I'll go through all 4 different ways to explain which way it moves. All right, we will go to 1:05. So 5, 4, 3, 2, 1. All right, so let's go in the order that we learned these. I have positive charges on the right. I have a positive charge. Opposites attract like charges repel. So it's going to be repelled by these positives and attracted by the negatives. So bam, it's going to go to the left. Opposites attract like charges repel. One of the first things we learned in this class. It's going to be repelled by these and attracted by the negative ones. It's going to go that way. Great. Next thing we learned about electric fields. Positive charges move in the direction that electric fields point. Electric field points to the left. It moves to the left. Another way to understand which way it's going to move, not with the wiggly line. So it goes in the direction of electric fields. That's one way. All right, what's another way we learned? I guess these last two kind of collapse together, so I guess it's only three ways. How disappointing. That things go to lower energy. So this one kind of collapses some ideas together. What is my energy at various locations? U equals Q times V. So take the charge of a proton, multiply it by the voltage, that gives you the energy. Here, I have a positive energy. Here, I have a zero energy. 0 times the charge, the voltage on the left side is 0. 0 times the charge is that. Which way is lower energy? To the left. It's going to go to the left. And the last one just kind of says that charges go from positive charges, go from high voltage to low voltage. Positive charges go from high voltage to low voltage, but because of the lower energy thing. So there you go. So many ways to answer this, and it uses all our ideas all together, connects voltage and electric field. All these things are interconnected. If I put a negative charge here, everything I just told you, the opposite will happen. I mean, it'll still be repelled by the negative charges. It'll move opposite to the direction of the electric field. It still will move to lower energy, but the lower energy is at a higher voltage because the charge of an electron is negative. So that therefore makes, if I do U equals Q times V, that'll be a negative joules. That'll be a 0 joules. Negative is smaller than 0. Anyway, just a great kind of putting all the pieces together, all the concepts into one little package. All right. I like this question a lot too. It's very wordy for a very simple answer. 2 plates of a capacitor are separated by a distance d. So let me draw this for y'all. Here they are. 2 plates are separated by a distance d. They have an electric field, E naught, inside of it. Give myself a little bit more room to draw this. So they're separated by distance d. They have an electric field, E naught. If I double the distance between the plates, what happens to my electric field? I'm not going to even draw an arrow for it. Is it half the original electric field? Is it the original electric field? Is it double the electric field? Is it 4 times the electric field? If I move these plates twice as far apart, what happens to my electric field? Oh yeah, I'm loving the answers for this. And the nice thing at this point, the first few weeks are rough, but the cool thing now is we get to take the information, actually use it in situations, and it's a good time. All right, we'll go to 135, so 15 more seconds. I'll go to 140. Give you a little bit more time to think about it. In 5, 4, 3, 2, 1. So I love these types of problems where I say, here's a situation, here's how a variable changes, how does that affect a different variable? The key is solving every single one of these. Anytime I give you a problem where I say, hey, here's a situation, something changes, how's that going to affect it? Almost every single one of these boils down to there's an equation that tells us as something change, there's an equation that will tell us that thing that we're solving for and what variables affect it. So, in this case, we're trying to figure out how the electric field changes. We have an equation for the electric field due to these planes. And you know what? Let's write it both ways. Remember, sigma here is Q over A. A is the area of the plates. Q is... And go ahead and stare at this equation for a little bit and see if you can have the epiphany. Nowhere in this equation is the letter D or distance or anything like that. So, this is a really weird idea, but again, it just pushes that idea. Infinite planes are kind of have this weird solution. We're assuming they're infinite planes, which is every plane I'm going to give you all. There is no dependent upon the distance between the planes. And again, that's going to be really weird, but that's what the equation says. Whether you like it or not, that's how you solve these types of problems. How does it change when the variable changes? Find the equation. The equation is the one that gives us the information. And again, don't stress it, y'all, if you're missing any of these quicker questions. Remember, at the end of the semester, I give you 75% of the points just for answering it. I grade them out of 75% of the points at the end. So any you get right is just bonus. It doesn't hurt your grade and any capacity. Yeah?
Like 2 slides before, what is that equation then?
Yeah, so that's a great question. There was an equation with distance. That equation, way up here, where are you at? So the electric field won't change, but the voltage will.
Or not that one, the next.
No, it's fine. Was it this one instead?
Yeah.
Yeah, so this one is actually the same as this one, just rearranged. So this one, all I did was I multiplied the distance over. But sure, we can look at this one, but the next one. But the E for a parallel plate for a capacitor is just sigma over epsilon naught. So what ends up happening is the electric field doesn't change, but the voltage does. The voltage will double. So if I instead asked this problem and I said, what's going to happen to the voltage between those two spots? It will actually double, which is kind of a funky idea because you didn't add any more charge. Why does the voltage double? If we connect voltage to energy, we had to actually put energy to move those plates apart. So we actually increase the potential. If I put a charge there, you will actually accelerate something faster if I move it that way. But the electric field is the same. Again, just separating electric field voltage, all that jazz, gets a little funky. The voltage, and I really like that you asked that because I can kind of talk about it. In this problem, electric field stays the same. So if I double the distance, my new voltage will end up being twice as big as my original. So the voltage will double. The potential will double. And therefore, if I put a charge there, I could actually make it go faster if I flung it across. The electric field is just this. So the electric field does not depend upon distance. The voltage does. The electric field doesn't depend upon distance. The voltage does. Great question. Love it. All right. So, using what we know. So we have this equation. There's just a big old derivation here. I'm going to walk through the steps here. Obviously, you don't need to know the derivation. But again, it's kind of cool to see that we can take stuff we know and make new things out of it. That's all physics is. We observe something in physics, and then we take some ideas and we combine them together and we find new things. So, great. The electric field here, we just said that. Sigma over epsilon naught. Fantastic. We're going to use that voltage equation. And we are just going to take that electric field and put it right there. All we did was replace E with that. So we replaced E. Let's go ahead and write this. So V equals ED. Replace E with that. So we get sigma over epsilon naught times D. All we're going to do now is replace sigma with Q over A, because that's the definition of sigma. So that's all I did here. I just wrote out what's already there. Okay. So this thing called capacitance, I haven't quite mentioned yet, and it's going to show up in this next slide. All I want you all to see for now is this kind of piece here. We're going to introduce something called capacitance now, and this is going to kind of get plugged into this. This whole derivation, it's a little preemptive, honestly. It should be after this one. So let's introduce capacitance, and we'll visit that. We're jumping ahead a bit. Capacitance, we make up something. Capacitance, here's the way to think about capacitance. Think of a word that sounds like capacitance. Capacity. Capacitance is how much charge I can store on a capacitor per amount of voltage I put on it. The more voltage, the more charge I can put on it. So capacitance is how much charge I can store in this thing. How big is my bucket? Or maybe a better way to view this, how big is my water balloon? How much water can I put in this water balloon? That's the way to think about capacitance. Except instead of water, it's charge. Now, if you think about a water balloon, the faster I shove that water in, the more I can put in. If you'll hook up a water balloon to like a drippy faucet, you're not going to fill it very much. You hook it up to something that's got a bit of pressure, a bit more water can go in. You hook that thing up to a hose with a lot more pressure, and you can even add more water to it. So it's how much charge per voltage. Charge per voltage. And then all we did at this point, so this little thing here, now I'll show you where that came from on the next slide, just came from voltage equals ED and plugging all that stuff in. But for now, I want you to introduce the idea of voltage before I tell you where this equation necessarily came from. So this is Q over V. This is kind of the base definition of it. Just, it's a made-up idea. How much charge can this thing store per amount of voltage I put on it? More voltage, more charge. More capacitance, more I can put on it. Bigger my bucket. And then this part here, this epsilon naught A over D, that'll come from the next slide. The one I started and kind of paused on. Epsilon naught A over D. A is the area of my plates. So let's draw a nice picture of this. So remember, this is two plates. One with negative charge, one with positive charge. The area here. So I'll add this kind of down here to make it clear. Area A is the area of the plate. Just one plate. Area of one plate. You don't take the area of both and add them, just the area of one plate. And D is the distance between the plates. And epsilon naught here, that's just a number. Epsilon naught is just 8.854 e to the minus 12 in every single problem. Always it's that. It's a constant. It's on your formula sheet. Okay? So, area here is just the area of one of these plates. D is the distance between them. Okay. Now I'll spend a few seconds explaining where this came from. I kind of started it and paused when I realized I haven't told you what capacitance is. So just to show you that I didn't make this up out of thin air, so I made this up. I mean, I didn't. Someone did. We made up this idea of capacitance, how much we could store on it, the amount of charge you could store per voltage. And then all we did, so there it is, there's our made up thing. We took the voltage from here, replaced it there, where V is. We replaced it with this thing that we found with equations that we do know. Q cancels. And if you ever divide them by a fraction, it flips. And that's where we get that equation from. The A goes up top, the D goes down bottom, the epsilon naught goes up top. Don't worry about this energy thing on the bottom yet. I'm covering it with my hands, but you can't tell because... Don't worry about this right now. We'll get to that. But it's here for funsies. That's the energy... Well, hey, yeah, see if you remember what U is. It's the energy stored in it. We're going to find that this is the energy stored in a capacitor. It's 1/2 Q times V. Notice that I've got three equal signs here. Literally all that's happening here is I'm just taking this equation here and making all three versions of it. So in the first one, if I solve for Q here, so Q equals CV, if I just take that and plug it right here, I get the next equation. If I then do C equals QV, is that the one I want to do? Is that going to get it for me? No, I ain't going to do it. This next one just comes from solving for V. So V equals Q over C. If I just take that and I put that right there, I get that equation. Whatever. We'll get to that. For now, showing it to you all. Don't worry about it too much. All right. There you go. We've already actually answered this because I had a wonderful question previously. Two plates of a parallel capacitor separated by a distance D with a potential V naught. If I double the distance between the planes, what happens to the voltage? Last time we did this, I asked what happened to the electric field. This time I'm doing it, I'm asking what happens to the voltage. Look at that. It was such a good question. Past me also thought it was a good question. We'll go to a minute. Yeah, we'll go to a minute 10. Give you all the time to think. All right, and 5, 4, 3, 2, 1. Okay. So, the way we're going to go about this is how we started the other one. So we said that the voltage, we're going to use what we talked about before, the voltage equals E times D. So again, I've actually already written kind of the solution for it. The voltage originally equals E times D. My new voltage equals E times 2D. Remember we said the electric field stays the same? So if I double the distance, that equals 2. That's a terrible 2. Equals 2 times my original. There you go. Let's see how we did. And it's okay if we got mixed responses. There you go. Great. It's way better than expected. I thought we'd get more mixed responses. So the voltage doubles, but the electric field stays the same. Fantastic. Fantastic. Okay. So this one, what happens to the capacitance in a parallel plate capacitor if we half the distance between the plates and double their surface area? And I'll be very kind to you all. Remember, the key to this is using the equation for it. Last time I didn't give you the equation straight up. The equation for capacitance, there's a couple of them. We have this one. We have capacitance equals charge over voltage. And with capacitance equals epsilon naught A over D. Choose the one that actually works. What happens to the capacitance if I half the distance but I double their surface area? Does my capacitance stay the same? Does it half? Does it double? Or does it quadruple? And all about just playing around with the equation and how the variables affect it. As the area goes up, what does that do to my capacitance? As the distance goes down, what does that do to my capacitance? And this equation reveals all the kind of how the variables affect it. But even without plugging in numbers, you can knock out 2 of the answers. Just by, if area goes up, what should happen? If distance goes down, what should happen? If you can just kind of understand that, even without the numbers, that'll help knock out a couple of them. All right, we'll go to 150. I'll go to 2 minutes. I see some people still thinking about it. In 5, 4, 3, 2, 1. All right, so let's go ahead and apply that kind of wordy thing I was saying. So our area goes up. So what's going to happen? Well, area is up top. So if that goes up, capacitance goes up. If it's in the numerator, as that goes up, capacitance goes up. Distance is on the bottom. If I divide by a smaller number, I get a bigger number. So area, increasing that, increases my capacitance. Making the distance smaller. Divided by a smaller number also makes it go up. So I got 2 things increasing it. And the question now just is how much will it go up by? We know it's going to go up, so that removes the stays the same, that removes the halves. Now we just got to plug in the numbers to kind of see what it does. But that's something you can do in solving these to kind of check if your answer makes sense. Where are my variables located? If it's in the denominator, it follows the opposites. As it goes up, the result goes down. As it goes down, the result goes up. If it's in the numerator, it doesn't. But we can also get it from the math here. So we have epsilon naught. My area doubles, so we put a 2 in front of it. My distance halves, so we put a half in front of it. We are very blessed with this equation that there's no squareds, so we didn't have to do anything like squaring one of the numbers. Previously, that was a thing that happened when we talked about electric fields and forces. If we divide by a half, that's the same as 2. So we get a 2 from the bottom, we get a 2 from the top, we get an epsilon naught, A over D, and we get 4 times my original. So the answer is it quadruples. But yes, I can guarantee, make certain you all go, each class it feels like we kind of do ones like this. Go through these, practice these. The reason for these is they give you a better understanding of what's happening. As I make my capacitor bigger, I can store more charge on it. Remember, what is capacitance? Capacitance is my capacity to store charge. If I make it bigger, I can fit more charge on it. If I decrease the distance, what that's letting me do is that is decreasing the voltage, and it's making it easier to kind of pile charge on there. So, all right. So yeah, how do we charge them? We stick a battery on them. So that's kind of the next step. Great. We talked about capacitors. We talked about what they are. How do you actually build charge on these things? You introduce a voltage. You introduce a voltage, and that voltage is going to start piling on charges. So remember, let's look at this battery here. This is kind of our first little view of a circuit. We have a battery. One end has a positive voltage. One end has a negative voltage. And we have a wire. This wire, you can almost just think of it like a road. It's more than a road, but that's kind of the way to think about it. And inside of this wire, it's metal. So inside of this wire is a bunch of electrons just chilling in the wire. Bunch of electrons chilling in this wire. The second that this switch becomes closed, it has to become closed, those electrons will see a potential difference. They will see a high voltage and they will see a low voltage. And remember, if there's a difference in voltage, charges move. Now I want y'all to spend a few seconds and think about which way will those electrons move. So in the wires, all these electrons, the electrons are the ones that move. This is an important concept that I'll repeat a bunch. Protons don't move because protons are literally the nucleuses of atoms, and that would mean that your nucleuses of the atoms, the literal atoms themselves, would be like moving, which would mean your wires would like move, which isn't what happens. So anyhow, the electrons are free to wiggle around. They're free to, jot around, jump around, especially in conductors. So see if you can guess which way will these electrons up top move, which way will the ones on the bottom move. And again, you can basically, these ones here see this negative voltage and they see this positive voltage. These ones up here see this positive voltage and see this negative voltage. And you know what? I'm going to make your all's life a little easier. Reminding to you all, if this is a 12-volt battery, we could pretend like this side is 12 and we could pretend like this side is 0. So when I said positive and negative end, one end is high, one end is low. I picked 12 and 0. I could have picked 24 and 12. I could have picked 112 and 100. As long as the difference is 12. All right, so yeah, which way will they move? Think about it. So, if you said counterclockwise, you're correct. Electrons do the opposite. They go from low voltage to high voltage. So electrons are going to want to go this way. They are going to want to go towards that positive voltage. Now, these ones up top have no problem doing that. Look, they got a nice pathway there. Now, as I pull electrons away from this, so this capacitor also has electrons on it. It's going to start pulling electrons away. And if I start pulling electrons away, this side's going to start to become positive. Because all a positive charge is an absence of negative charges. A positive charge just means I've taken away electrons. Again, we can't take away protons. It's not happening. You can't rip apart an atom and start yanking protons out of it. We can take away the electrons though. So anytime something's positively charged, except for protons themselves, it just means we took away electrons. All right, what's going to happen on the bottom? These electrons are going to pile up on here, but they cannot jump that gap. This is an insulator. Between that is an insulator. Insulators, electrons cannot flow, so they pile up. And behold, I need to make sure my numbers are consistent. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. They end up with equal but opposite charge. The negative charges pile up on the bottom, and on the top, they kind of get sucked out of it. And you end up with that situation, two parallel plates with opposite charges. All we had to do was introduce a place of higher voltage and lower voltage, a place of lower potential energy and a place of higher potential energy. That's all a battery does in your all circuits. Anytime you plug a battery into a circuit, you are just introducing a location with lower energy and higher energy, and the electrons are going to start to go to that lower energy. That's what a battery does. That's what plugging something into the wall does. Your wall introduces 120 volts, 120 high. Technically, it's going up and down and up and down and up and down, but there's a changing voltage of 120. 120 high, 0 low. A height difference, if you will. All right. We're going to see that a bunch. So if that didn't make sense now, we're going to see it a lot. Okay. So anywho, that's not going to happen forever. It's not going to keep sucking them away forever, because as this thing builds in charge, it's going to build in voltage. Another way to think about this, I can't keep shoving negative charges on here infinitely. At some point, they're going to get repelled with the same force they're getting pushed on. Again, another example for y'all. This is why charging your phone battery, it gets slower. The more charges you shove into your battery, the harder it gets. The more charges we shove on this capacitor, the harder it gets to charge, because it's literally more of them stuck together. They don't want to be together, but it's more favorable than being in the here for now. But as time goes on, they'll build and build and build and build. And when does that end? When the voltage of the capacitor is exactly equal to the voltage of the battery. And what have we resulted in here? If this side is 12 volts and this side is 0 volts, now this side is 12 volts and this side. Let me double check to make sure that makes sense. That it's that one. Yeah. It is no longer advantageous for electrons to go from this side to this side. 0 to 0, there's no longer a height difference, voltage difference. On this side, it is no longer advantageous for electrons to go from one end to the other. There's no longer that height difference. So again, I keep saying the word height because that's how you can think about voltage. It's kind of like a height. Things go downhills. Electrons go from high voltage, low voltage to high voltage, which is weird. They kind of like roll up the hill, as weird as that sounds. Anyway, they go to lower energy. So, long story short, what's the takeaway? If you charge a capacitor, it gets the voltage of the battery. That's the takeaway here after all that jazz. Okay. Now this is the last thing. How do I get the energy stored in a capacitor? 1/2 Q times V. And I'll spend a little bit of time on this. Okay. Where did this come from? It did not come from thin air. This came from this. You're not going to like this. Came from this. But guess what you would actually have to do to find this? If you don't know, that's an integral sign. More calculus! It's gone. So if this was a calculus-based course, I would do the integral and show you all that this equation with this half. So the one I gave you all before, the energy that a point charge has is QV. The energy a capacitor has is 1/2 QV. You best believe some of you are going to use the 1/2 when you shouldn't. So be very careful here. This is for a capacitor. Capacitor. This is for a point charge. So this is something that you may want to put on your note card if you think you're going to make this mistake. Because on the formula sheet, they both get called UE. If you think you're going to mix up which one's which, you can label them on your thing. We'll spend more time on this next time. But for now, I just want to show it to you. So that's the energy stored in a capacitor. That's the energy a point charge has. They look identical. This one has a half. This one doesn't, because this is a point charge and this is a capacitor, and they're not the same thing. So next class, we'll derive the rest of these. We'll do some math. We'll talk about resistance. So we kind of got through capacitors mostly today. Yeah, y'all. We're in this. I don't know. I enjoy this stuff more because we've gotten through, in my opinion, the worst of it. As weird as that sounds, being only 3 weeks into class. But if it was still hard, spend the time, y'all. Polish up those electric fields and forces because they are tricky. And clearly, we're still using them.